Could a mountain rise up into space? Well, to answer this question, we first have to define at what altitude space begins. There are one of three definitions we could use. The first is the thermopause, or where the thermosphere ends and the exosphere begins. The thermopause can be between 500 and 1,000 kilometers above sea level, and at this altitude, a molecule has a 50-50 chance of either flying off into space or remaining in the atmosphere. Above it, in the exosphere, a molecule is more likely to escape into space, and below it, in the thermosphere, it is more likely to remain in the atmosphere. The next is roughly 160 kilometers above sea level, and this is the minimum altitude at which an object could orbit. Below this altitude, air resistance would slow down satellites, causing them to fall to Earth. The third and lowest definition of the start of space we could use is the Armstrong limit. And no, this isn't named after Neil Armstrong, but Harry Armstrong, the former Surgeon General of the U.S. Air Force who first recognized it. As the pressure decreases, the boiling point of water will also decrease. The Armstrong limit is at 18.3 kilometers high, where the pressure is 6.18% that of the air at sea level. Here, the boiling temperature of water is about 37 degrees, i.e. the human body temperature. This means that above the Armstrong limit, you'd have to wear a pressurized suit because the atmosphere would kill you as quickly as space would. At this altitude, the sky becomes noticeably darker as well. So, could a mountain theoretically reach any of these altitudes? Well, as rocks are piled on top of each other to form mountains, the rocks at the base are subjected to greater and greater pressures. This causes these seemingly rigid structures to become deformed. At a certain pressure, their elastic limit will be overcome, and they will start to act as a liquid. At this point, if you add more material onto the top of the mountain to make it taller, the rocks at the base will flow away, causing the mountain to sink at the same rate it grows, which ultimately limits how high they could get. The average elastic limit of rocks is 3 times 10 to the 8th newtons per square meter. The amount of pressure rocks above it will put on a rock at the base of the mountain would be their density multiplied by the height of the mountain multiplied by the acceleration due to gravity. The average density of continental crust is 2,700 kilograms per cubic meter, and the acceleration due to gravity on Earth is 9.8 meters per second squared. So, if you crunch the numbers, we get a theoretical maximum mountain height of roughly 11.3 kilometers. For some perspective, the summit of Mount Everest is 8.85 kilometers above sea level. 11.3 kilometers is 7 kilometers short of the lowest definition of space, so on Earth, there's no way a mountain could reach space. But what about on another planet? Going back to how we calculated the theoretical maximum height of a mountain, if we have a lower acceleration due to gravity, a given mass above them will put less pressure on the rocks at the base. So, if we had a planet with half the gravity of Earth, then a mountain could be twice as high, i.e. 22.6 kilometers, and thus reach the Armstrong limit, right? Well, not really. You see, the atmospheric pressure at a given altitude is determined by this equation, where P0 is the pressure at the surface, what we call sea level, multiplied by E to the negative altitude divided by the scale height, or h. On Earth, the scale height is roughly 8.5 kilometers. The scale height is equal to the product of the Boltzmann constant, 1.381 times 10 to the negative 23, and the temperature, divided by the product of the acceleration due to gravity and the average molecular weight of the atmosphere. So, if the gravity is half that of the Earth, the scale height would be doubled, and the Armstrong limit would also be twice as high. So, on a planet with the same surface atmosphere and half the gravity of the Earth, a mountain couldn't reach space either. Basically, the lower the gravity of the planet, the slower the atmospheric pressure will decrease as you go up in altitude. But we could also tweak the atmosphere a bit. One way to make the Armstrong limit exist at a lower altitude is to have the atmospheric pressure at sea level be lower. The atmospheric pressure at the summit of Mount Everest is 34% of that of sea level, 5.5 times the pressure of the Armstrong limit. So, if we were to tweak the atmosphere to make the Armstrong limit exist at the highest mountain, the surface pressure would have to be 18% that of our own atmosphere. Now, you might think that we couldn't survive on such a planet. However, the minimum partial pressure of oxygen we need to survive indefinitely is 0.118 atmospheres. So, if our hypothetical planet had an atmosphere composed almost entirely of pure oxygen, we could survive on the surface, yet still need a spacesuit to climb its version of Mount Everest. But going back to the equation for scale height, how else could we tweak the parameters? Another way is we can alter the temperature. Since the temperature is part of the numerator, the colder the planet, the smaller the scale height, and the faster the atmospheric pressure will decrease with altitude. In order for a planet with the same surface atmospheric pressure at sea level to have the Armstrong limit at the summit of Mount Everest, the scale height would have to be 3.18 kilometers, 2.67 times less than that of Earth. The average surface temperature of Earth is 288 degrees Kelvin, so the temperature of the hypothetical planet would have to be 108 degrees Kelvin to have the appropriate scale height. This is above the boiling points of nitrogen, oxygen, and argon, so such an atmosphere could exist, but liquid water would not be present on the surface, so it's not a planet humans could inhabit. Instead of the temperature, we can also tweak the atmospheric composition. Remember, the greater the average molecular weight of the atmosphere, the smaller the scale height, and the faster the pressure will decrease with altitude. One of the heaviest gaseous elements is xenon, with an average atomic weight of 131.3 grams per mole. So, on our hypothetical planet, instead of being composed of 78% nitrogen, 21% oxygen, and 1% other, the atmosphere is still 21% oxygen and 79% xenon by number of atoms. The average molecular weight of the air would be 110.4 grams per mole. By contrast, that of Earth's atmosphere is 28.96 grams per mole, so this atmosphere would be 3.18 times heavier than ours. The scale height of the hypothetical atmosphere would be 2.23 kilometers, so the Armstrong limit would exist at 6.2 kilometers. This is below the summit of Mount Everest, so on such a planet with an atmosphere, a mountain could quite possibly go into space. Also, the maximum altitude a human could survive indefinitely would be at 1.29 kilometers above sea level. But could such a planet exist? My tentative answer would be no. First, xenon isn't that abundant, so I doubt it could be the main component of a planetary atmosphere. Second, the reason we don't see the chemical composition of our own atmosphere change very much with altitude is that its major constituents, i.e. argon, nitrogen, and oxygen, have a similar molecular weight. However, xenon is much heavier than oxygen, so it will mostly sink while the oxygen will rise. This means that if the surface was to be breathable, there would have to be some pretty strong vertical mixing forces to keep the atmosphere homogeneous. But I could be wrong, and if anyone who studies planetary atmospheres knows of a way an atmosphere could exist, please let me know in the comments. Also, I know there are many other factors which likely limit how high mountains could get. The one I used is easiest to calculate for this fun little thought exercise.